Hi everyone, welcome to this iChemie Process Management and Control Special Interest Group presentation. So this is going to be a presentation on the technology using optical fiber-based distributed sensors with a focus on distributed temperature and acoustic sensing. There will be a review of applications where monitoring systems are used today, including reservoir management, environmental and process monitoring, with emphasis given to seismic survey acquisition and pipeline surveillance deployments. My name is Zaid Rawi from BP, and our presenter is Dr. Michael Mondanos, and he is the Vice President, Industrial Applications with Silixa, and he joined the company as a Business Development Manager for Industrial Monitoring Applications in 2011, and prior to that he worked a number of years in the field as a Senior Engineer and Project Manager. Michael holds a master's degree in communications and radio engineering from King's College and a PhD in optical fiber instrumentation from Imperial College, University of London. And he's responsible for expanding upon Silixa's position as a leading provider of distributed sensing technology into larger scale projects servicing the downstream oil and gas and pipeline sectors, whilst continuing to grow Silixa's presence outside the energy industry as well. He's authored several international publications and is an acknowledged expert within the energy industry. We will take questions at the end, but please feel free to type them into the question pane during the presentation as they occur to you. Very good. So Michael, I will hand over to you now.
Thank you very much. Good afternoon to those attending this webinar that has been organized by the Process Management and Control Special Interest Group. Now, before we start this technical talk, I'd like to thank Audrey and Zaid of the iChemie Group for setting up the webinar, as also my colleagues at Silixa for the contribution of the technical material. I'm the Vice President of the Pipeline Industrial Sector at Silixa, looking mainly after sales and application development. My background is optical fiber, as I mentioned before, and the subject of this talk is going to be about optical fiber distributed sensing. Now, the subject is quite wide. What I've tried to do over the next few slides is to capture the basic principles of distributed sensing, and will describe some of the core applications within Silixa. I'll also describe the functionality and the applications. Now, I've set up my email address. If we don't have enough time, you can email me with any questions in any inquiries you have. Now, today's webinar is summarized by the outline topics shown. We will start with a basic introduction to the technology. We'll give you a brief company overview, and we'll move to the technology fundamentals. I will introduce some core application areas, and we'll conclude with an extended description of the pipeline monitoring applications, what we offer at Silixa. The first slide is about just an overall of the optical fiber sensors. The optical fiber was used for the first time in late 1970s as the preferred medium for long-haul optical communications, mainly due to the high bandwidth capacity and low losses. In the early 1980s, we saw the first application of optical fiber sensors. The optical fiber offers a number of advantages for applications in monitoring, critical infrastructures, in oil and gas, energy, civil engineering, and security sectors. The main advantage of using optical fiber is actually the range and the fact that no power is required over several kilometers. In our applications, the optical fiber is the actually sensor, and there's one interrogator at the other end where monitors the back reflections, what is coming from the fiber. There are a number of optical fiber sensor topologies and architectures. Today, what we're going to focus is mainly the distributed temperature sensor and distributed acoustic sensor. Both of these are types of intrinsic optical fiber. Other fiber sensor families can be seen on the diagram. The main advantage, why do we select the distributed sensing over point sensor? is based on the fact that the important features of the physical property or measure may be missed during using conventional point sensors. The optical fiber provides a special distribution of measurements that enables the capture of details along the infrastructures. Point sensors at best can be deployed over several hundred meters, while the optical fiber sensors can be deployed over kilometers, tens of kilometers of monitoring the infrastructure. The point sensors are discrete measurements. We need to interpolate between the measurements to get the complete profile. With the optical fiber, with the distributed sensors, we gain a continuous measurement of the infrastructure, and we can capture all the information along it. Before we examine the fundamental principles of the technology, I will introduce briefly our company and the main application served sectors. Silixa was established in 2007 to develop and commercialize distributed temperature and acoustic sensors predominantly for the oil and gas sector. It has received funding from the Limebrook Partners, Chevron, and Statoil. Silixa today has over 60 employees. It has operation facilities in the US and in the United Kingdom. The manufacture of the monitoring equipment takes place in the United Kingdom. Silixa has established partners across the globe, runs operations, and has installation across all continents. In addition to oil and gas applications, Silixa supports and develops applications also in other sectors today. The main core application sectors are the oil and gas and pipeline surveillance. In Silixa, during the last few years, we also find a number of inquiries coming from other industries, and we supply equipment for geothermal, dam, power, and process monitoring application. It has also established a number of relationships with research institutes and organizations aiming towards the development of future applications and products. In oil and gas, the monitor equipment are used for seismic surveys, well integrated as also production and fracture monitoring. In pipeline, we use both the acoustic and temperature system for leak detection, while the acoustic system is used for intrusion detection. Next item on the agenda is going to be the introduction to the technology fundamentals. We'll start with the description of the fiber types used, and we'll move to a description of the sensing processes and introduction of the main features of the equipment we use in our applications. There are two main optical fiber categories. These are the single mode and multi-mode fibers. There are two types of multi-mode fiber. In single mode fibers, the propagating light wave forms a single optical fiber mode, while in the multi-mode fibers, there are many optical modes. Propagation is ensured by total internal reflection based on the difference between the refractive index between the core and the cladding. The three main fiber types shown on the picture with the basic description of the refractive index profile of the silica fiber. The difference between the cladding and the core refractive index is achieved by doping the cladding with different materials. In our applications, we use both the single mode and multi-mode graded index fiber. All fibers are standard, widely available fibers and used for communications. To see, the fibers are encapsulated with a protective layer outside the cladding and bundled together in various cable constructions. A typical fiber cable construction is shown. It includes several protection layers and multiple fibers. These cables are very strong and can be handled in a similar manner to electrical cables. In downhole application in the oil and gas industry, the construction of the fiber is mainly based on several layers of steel tubing. To describe the principles of distributed sensing, we need to examine the different optical fiber attenuation mechanisms. The main mechanisms in the fiber are scattering from the glass molecules and lattice formation, as also the absorption at specific wavelengths and external effects to the fiber that are related to fiber joists and splice connectors. Where interesting to the fiber losses caused by scattering. There are three basic scattering effects, named as Rayleigh, Raman, and Brillouin. In Rayleigh scattering, photons scatter from an atom or molecule and most photons are elastically scattered, having the same frequency wavelength as the incident photons. In Raman scattering, photons are scattered by the effect of vibrational and rotational transitions in the bonds between the first-order neighboring atoms, while brilliant scattering results from the scattering of photons caused by large-scale, low-frequency photon. Where phonon is a quantum mechanical description of elementary vibrational motion in which a lattice of atoms or molecules uniform oscillates at a single frequency. We'll move to the next slide, and it gives you a pictorial description of the different scatter mechanism in the fiber. We have the incident light, which is indicated by the arrow in the middle of the screen, and we get the Rayleigh reflection at the same wavelength as the incident light, and then we get the brilliant and Stokes and anti-Stokes components. We also get the Raman Stokes and anti-Stokes components. The Raman anti-Stokes band is temperature sensitive. So if the temperature of the fiber changes, the back reflection, the energy of the back reflected signal increases. The intensity of the Raman Stokes is used mainly as a reference. The Ultima is the trade name for a distributed temperature sensor. It's a system constructed in the following manner and sends a laser pulse down the fiber. This is a standard optical fiber. We use a multi-mode gradient index fiber with the Ultima DTS, although we can also interrogate a single mode fiber. The DTS monitors both the Stokes and anti-Stokes components of the backscatter light and calculates the temperature as a function of time. The output from the DTS, we capture both the Stokes and anti-Stokes Raman scatter detecting amplitudes as a function of distance. And within the actually unit, we calculate the temperature profile. The principle we are using to accurately locate the different events across the fiber, the different temperature events across the fiber, it's a technique called the time of flight. And this is we trigger the optoelectronics, the detection of optoelectronics. So when laser pulse sent from the DTS, we start a timing process, and we detect both the Stokes and anti-Stokes parameters as a function of this time. The main the amplitude, the performance of the DTS, of the distributed temperature sensor, is often measured with respect to the temperature resolution that defines the noise levels in the smallest increment that can be identified as a function of measurement time, and also with the spatial resolution. The spatial resolution is a function of temperature and length. It defines the ability of the instrument to detect accurately a temperature event. This graph shown on the right of the screen has taken from our test facilities, and this is what we do to characterize the spatial resolution of the unit. It's quite different to the sampling resolution of the unit. Often it's about twice the sampling interval. So we use a hotspot, or we use a temperature event of about 30 degrees in amplitude, and we try to identify how much, what is the length of fiber in order to needed to detect this 30-degree hotspot. The data is shown here for the Ultima S. This is a 5-kilometer range DTS unit. Distributed acoustic sensing works in a similar way. However, in this instance, we're interested in backscatter light, which is affected by dynamic strain within the optical fiber. In the absence of other influences, these tiny stray events caused by sound waves interact with the optical fiber. Once the pulse of laser light has reached the end of the fiber and reflected back to the interrogated, the fiber can be considered as dark, at which point the next short laser pulse can be injected. This process is repeated roughly 10,000 times per second on a 10-kilometer fiber. The results in acoustic signal sampled at 10 kilohertz. Higher frequency sampling rates can also be achieved at the shorter optical fiber lengths. The acoustic samples are mapped to the fiber distance again based on the optical travel time. The IDAS data is highly sampled in both time and space, and so a common method of visualizing the data is a time domain, or what we call a waterfall plot. This is shown on the left, where the x-axis is the fiber length and the y-axis is the time, shown here for a period of 45 seconds. The color scale indicates the acoustic energy levels, with red being the highest, the loudest. On the right-hand side, we can see one sampling point, one channel, as we often refer, and we see in time the acoustic wave. We'll come to the end of this session and summarize some of the key performance specifications we have for the equipment we manufacture and actually the equipment we used in our applications. In acoustic monitoring application, we use the IDAS. The I stands for Intelligent Distributed Acoustic Sensing, and senses through acoustics. It detects the amplitude, frequency, and phase along the optical fiber at every sampling interval. It has a high dynamic range and a frequency bandwidth from starting from millihertz up to about 100 kilohertz. The system can be used with both multi-mode, graded index fiber, and also with single mode fiber. In temperature monitoring applications, we have the Ultima with a resolution that can go down to 0.01 degrees Celsius. It has a quite fast response of 1 second, and the best sample resolution we can achieve with the unit is about 12.5 centimeters. These units have a range up to 35 kilometers. Now, we also offer a version of the Ultima for single mode fibers. Now, the latest addition to the family of the temperature monitoring equipment is the XT-DTS, which is quite a ruggedized unit and is used in harsh environments. It has an operating range from -40 to +65 degrees. The range for this unit is 10 kilometers, and it's got a tunable range, so we can adjust the performance of the unit at the 2, 5, and 10 kilometers. This unit is a low power operating unit and can be powered from batteries in the field. Now, we're going to move now to some of the actually applications, and I'm going to start with the DAM Seepege detection application. This is one of the first applications I got involved early in my career, and I had the opportunity to work on a number of installations, mainly in the north part of Europe. And in these applications, the DAM is quite a long infrastructure, and it's very difficult to monitor for seepage events across the whole DAM. They need continual monitoring. Some of the problems, as I said before, is the seepage, but also it's also the formation transverse sinkholes, or what do we call the piping events. One of the techniques that's being used quite extensively today is based on passive temperature measurements, where the temperature along the downstream part of the dam is monitored and compared to the reservoir temperature. On the top right corner, you will see the simulation of the temperature, how the temperature travels from the reservoir all the way to the downstream part. So what do is we developed one of the companies we're working very closely have developed a model, and they expect the response to expect the expected response at the downstream path. Usually what we do is we install optical fiber cables along the downstream, even on the crest, and we monitor the temperature at very close intervals across the whole dam. The information we get at every single sampling point is fitted into the expected response that comes out of the different simulations and models. And what we do is we alarm in the cases where there is a deviation from the expected response. Here you see the downstream path of an embankment dam, where you can install optical fiber cables at different locations across the berm of the dam, but also the optical fiber cables can install in boreholes. The equipment monitoring is shown on the left-hand side, monitoring continuously the temperature, and then after a calibration period, they can provide flow rates, seepage flow rates at every sampling interval. Moving to the next application, it's about high power, high voltage power cables, where the fiber is either included on the voltage cable or is strapped or attached to the power cable and provides continuous information on the skin temperature that is related to the cable current load. Using real-time thermal rating software, it is possible to predict in real-time thermal bottlenecks and overload conditions. The Silixa solution provides fundamental monitoring in the case of circuit maintenance and reinstatement regimes. Under such conditions, the network transport link can be more heavily loaded that would take under normal conditions. Again, this is a distributed temperature monitoring application. What we're planning in the near future is to actually use a distributed acoustic sensor to monitor for unplanned third-party intervention on the network's critical transmission links. On the next slide, again, this is an application I got involved in the early, around 2012, where we installed the optical fiber cables using special structures around process vessels. These images are from a refinery where we had to install the optical fiber cable in order to detect the temperature surface skin. It was almost impossible to use any other technology, and optical fibers provide the only solution. We have done some preliminary modeling where you can actually see the optical fiber sitting in the middle. The fiber, with the help of a panel, was pressed across the walls of the vessels, and we monitor the response to adjust the measurement time and the sampling intervals on the Ultima DTS. Now, the information, we continuously monitor the temperature information, and what you can see here on the top right-hand corner is actually the formation of a hotspot that was created along the vessel. This was done during the factory acceptance test, and the system will detect these hotspots and will send alarms through a Modbus links to a SCADA network, or it will also allow the operator to visualize in real time the temperature distribution of the of the surface skin. Now we move now to in-well applications, and just to give you, before we take some of these applications, just to have a look on how the cables, optical fiber cables, are installed in boreholes. In the first picture, you can see the cables is installed inside the tubing. This is used mainly in wireline operations. On the second slide, the actually optical fiber cable is strapped to the outside tubing. It's also the outside production or injection tubing. And the third image, the optical fiber cable is installed behind the casing and clamped and cemented. You can see some images from a typical installation. The conditions are quite rough and it's quite a harsh environment, but in all the applications, in all the installations we're running today, the cable, the optical fiber cable has installed successfully. You can see in the mid picture, the cable below the tubing hugger. These are quarter-inch stainless steel constructions, and they can withstand extremely harsh environments. We have applications where the optical fiber cable can go up to more than 10,000 psi pressures and temperatures up to 300 degrees Celsius. In the next example, it's one of the applications where we run a wireline optical fiber cable. So the cable is lowered. The cable is lowered inside the production tubing of an injection gas well. And we use this application to monitor the injection of the gas, but also to get the information about the integrity of the production tubing. You can see on the right-hand side how the temperature profile changes. It moves from a geothermal gradient to a temperature has been affected by the injection of the gas, and once the gas injection has stopped, then the geothermal profile, the temperature of the production tubing follows again the geothermal profile. In this example, the well was about 3,000 meters. The well was about 2,000 meters. We had about 1,000 meters of surface cable to get to the well, and data was sampled at 12.5 centimeters. In the next, this is an application where we integrate both DTS and IDAS, the measurement techniques, for basic production and well performance monitoring. A fiber optic cable with 2 fibers minimum, the one for the DTS and one for the IDAS, installed in a well, and where we can monitor both the acoustic and the temperature response during production. Each block of data is processed into a single image showing current and differential temperature, as well as acoustic RMS value across the frequency spectrum. Static depth-based data, such as deviation and gamma ray, can be plotted alongside, and time-based data, such as downhole gauge outputs, plotted underneath to support the interpretation of the data. Since each 1-minute block is presented by a separate frame, they can be viewed in succession or animated to create a quick view of dynamic well conditions. The seismic version of the IDAS is designed to measure in a moving window the relative strain between 2 points on the fiber 10 meters apart. The system response is linearly proportional to the average fiber elongation along the gauge length. Here we see the seismic profile produced by 1 kilogram of dynamite source, the vertical seismic profiling profile in carbon capture and storage well. The cable has been cemented behind casing in an observation well and over a depth of 2.8 kilometers. The application for this acoustic sensing provides instantaneous measurements across the entire depth of the well, using single seismic shot, and tests can be repeated over time without the need of intervention in the well. We complete some of the examples, and we're going to move more now to the pipe surveillance, the pipe monitoring application, where we had received a large number of inquiries the last couple of years. As the technology matures, more and more operators want to install surveillance and monitoring fibers along the construction, along the infrastructure. What do we do at Silixa? We identify the monitoring requirements. We do some modeling work and customize the system. Then we test the performance of the system. We do in our test facilities here in the UK, and then we can also do excuse me, a site performance characterization. We have a test facility. We have several sections of pipeline buried in the ground. We have leak locations around the. We create potential leak locations around the pipe sections, and we can simulate a number of tests. This is actually data, leak detection data based on field data, and this application is using distributed temperature sensing. We can allocate different zones. We use a number of different leak detection algorithms. Depends on the location. We have system alarms based on the operation, on the communication, also the fiber break, and we can build different interface modules to connect to the SCADA system. This is a typical performance for the distributed temperature sensor. Again, there's so many different performances. These are characteristics. The first one is based on the fluid leak detection with a temperature difference of 4 degrees and a flow rate of 1 liter per minute. It will take approximately about 120 minutes to detect the leak. You can see on the right-hand side the actual formation of a leak event. We managed actually to detect the event a lot faster, but we managed to identify a leak at about 8 kilometers away from the monitoring equipment, and we triggered an alarm with a loss of less than 1 barrel. On the intrusion detection, we use the distributed acoustic sensor. Different events create an acoustic signature. They create they change the strain on the actual optical fiber cable. We detect the acoustic event, and you can actually see the waterfall of this from a digging event. And once we detect and classify the actual event, we can localize the event as a distance along the optical fiber cable and from the optical fiber cable, and then we map the event and on using our security management surveillance system. Here you can actually see the intrusion, the intrusion event, the car from the signature from a car. You can see at a time instance across the channel how the response of the acoustic signals with respect to timings, and also you can visualize across a number of channels, across the sampling intervals of the optical fiber cable, and you can see the different frequency components. So we collect this information, we track the event, and based on the frequency spectrum, we can actually classify the potential, the event close to the optical fiber cable. On the intrusion events, some typical performance specifications are given on this slide. We can detect walking about 5 meters away from the cable, manual digging about 15 meters away from the optical fiber cable, a small digger 25 meters, and a power vehicle activity around 20 meters. Again, all these parameters depend on the optical fiber cable used, the installation, and the ground conditions. Typically, we install the optical fiber cable at about between 0.5 and 1 meter below the surface. You can visualize the intrusion detection. We use our intrusion detection application. We can plot along the map the different events. We give information about the alarm time, what the class of the event, the severity of the event, and of course the actual location. These are images from these are images from actually installation in Nigeria that was completed a few days ago. You can actually see the the optical fiber cable is installed next to the pipeline. There was a 55-kilometer crude export pipeline, and we included for that installation both leak and intrusion detection. The next slide, I mean, before we actually commission the complete pipeline, 2 intrusion events were detected, and you can see these are photographs taken from the field, and where they tried to actually tap into the pipeline. And I'm just going to close the presentation, just showing about the different potentials we offer across the pipeline. We use 2 independent methodologies for the protection of the pipelines, the monitoring of the pipeline. They're based on distributed temperature sensing and distributed acoustic sensing. We use thermal leak. We can use thermal leak and acoustic leak detection, and also we can include an acoustic intrusion detection across the pipeline. Now, there are additional services which are working on, and these are based on monitoring of natural hazard across the whole pipeline, but also a service we're offering to track operations like pigging, because in a number of pipeline services, the pigs were actually lost within the pipeline, and meant that the actual operator had to spend a lot of money and time to identify where it is. And this brings us to the end of the presentation. And I know, Zaid, if you want to coordinate some questions. And thank you very much for attending.
So we have a few questions already, Michael. So the first one is from Fergus Harrison. This was about 20 minutes into the presentation. He was interested in seeing more detail about the environmental specifications for the fibers.
Okay.
What kind of things can it cope with? You've obviously touched on that a few times, but maybe just to summarize.
Yeah, environmental, well, the fibers, well, of course there are glass fibers, okay? The fibers come with different protection layers. Now, the primary protective layer can be a polymer, which makes the fiber be able to withstand up to about 70 to 80 degrees Celsius. And then we can go to high temperature acrylate, which means the fiber can go up to 150 degrees Celsius. And then we can go to different coatings like polyamide, that it can take the fiber up to 300 degrees Celsius. Now, I have used in some applications where we had a very high temperature environment, gold coatings on the fiber. We can go up to 600 degrees Celsius, but I think this is the absolute top limit. I mean, temperature is the main factor that affects, that defines the construction of the encapsulated the fiber protective layers. And then, of course, we go to different. We can go to steel tubings. We can go to incolloid tubings. It depends how corrosive is the environment. So there's quite a lot of advances in the cable manufacturing business, mainly because of the optical fiber sensing applications.
Yeah, I guess the claddings are of all different costs, and some are more custom than others. Is that fair?
The core and the core and the cladding are, let's say, in a way, set up as standard.
Sorry, the ruggedized cabling, I should probably say.
The ruggedized. I mean, if you see, I mean, think about this. There are transatlantic cables installed in the early 980s, and this can withstand really, the cables are buried in very deep environments. Also, there are so many optical fiber cable installations in oil wells, and the environment there is quite corrosive, high temperature, high pressures. So different encapsulations for different applications.
Very good, thank you, Michael. So just as a reminder, if anyone has any questions, feel free to type them into the question pane, and we will read them out. So there was another question from Fergus about the maximum skin surface temperature that can be monitored. I think you probably already addressed that just then. What's the highest temperature you've actually done on a reactor, say?
I've done 600 degrees Celsius.
Okay, all right.
This is with the
Sorry, go ahead, Michael.
The application we've seen, the process monitoring, these vessels, the maximum temperature was set up at 300 degrees Celsius, but we have tested up to and monitor temperatures up to 600 degrees Celsius. But again, the fiber cost, it's an issue there.
Yeah, and I guess it depends on how long you're doing it for as well. Perhaps maybe a short burst of temperature versus long temperature. Okay, and we have another question from Bill Clarkson, which is kind of the opposite of this. So he's saying multi-point temperature monitoring would be of interest to gas processors. Do you have examples of low temperature applications, particularly for low pressure vessels, skin temperatures?
Okay, low
temperature.
No, I've tested. We have tested systems, and we installed a system in at the LNG farm where the temperature can go down to minus 180 degrees Celsius. Now, in these sort of applications, we can't go to extremely long ranges. The response has to be tested, because the response we get from, let's say, the response we get from Stokes and anti-Stokes is quite low, maybe because it's low energy levels. Now, the fibers we can use at these sort of environments is similar to the fibers we use at the high temperature environments. So I will say we've tested the fibers down to 180 degrees, minus 180 degrees Celsius, over 400 to 500 meters. All the sensors, the DTS, the temperature sensors, are calibrated from minus 20 to plus 280 degrees. For low temperature applications, we need to specially calibrate the instruments.
Okay, thanks, Michael. I'm guessing you've got white papers for many of these applications, so presumably you have them on the website, or maybe if somebody emailed you, you could provide that.
Yes, of course. Yes. Yeah. We have some white papers here.
Okay, another interesting question from Fergus Harrison. So he's saying, if used in a refinery or a chemical plant process environment in, say, a safety application, which might mean you're taking formal credit for risk reduction or as part of an emergency shutdown system or safety instrumented system, has there been any work to have this SIL certified, so safety integrity level certified, so formal risk reduction by using this sensor?
Now, for the systems we have, the systems you've seen right now are operating on Windows. Okay, so depends on the safety integrity level required. I know for safety integrity level number 2, this might not be good enough. Okay, so in most of applications, because you're using the optical fiber as a passive element, the system it's at a distance from the measurement, and also we can deploy using redundancy techniques. So the safety integrity level, it's just a question, depends on the application.
Okay, so maybe one for follow-up.
Yep.
Okay. Then we have a question from Sonal Bajpai. So he's asking, in which situation is outside clamped wire preferred?
Sorry, Zaid, can you repeat that? I didn't understand that question.
I think he's talking about how you attach the fibre. So he's asking in which situation you would clamp it on the outside, I guess.
Okay. We're talking about in boreholes. So in the cable is clamped on the production tubing or injection tubing or observation tubing in installations where the well has already been drilled and it had been constructed. It's like a semi-permanent installation, because every time, when they want to service the well, they pull the production tubing, then the cable needs to come out and be replaced. Okay, so we clamp the cable when the well has been constructed, and the work is required after the well has been constructed, and it's included in wells where depends what we're trying to detect, what we're trying to measure as well. Behind casing, from what I've seen from our applications, is mainly used for seismic purposes and some leak detection. Inside the production tubing, we can get more information on the well deck, as also other components like valves included in the borehole.
Okay, thanks, Michael. So then we have a question from Mafue Onakpoya. He's asking, this is a clever question, will detection systems on pipelines work on pipelines that are buried in swampy terrain, and does it even work in water?
Okay, in swampy terrains, that's an interesting question, because what will change, the fiber optic cables will change, depends what is transported in the pipeline. And what are we looking for? Are we looking for some leak detection? Are we looking for intrusion detection? If it's gas, the gas when it leaks creates a very low temperature event. So it can be detected by optical fiber cable as a leak. Now, for intrusion detection, the cable needs to be in close proximity to the area. And we have working applications where the cable is buried was installed in the seabed, and will detect whatever happens around the actually fiber optic cable. It just needs some additional calibration. Yes, the cable will still work. We need to customize the cable type to protect it against water ingress, and so we need to have a correct construction, and of course the installation techniques used are going to be a bit different.
Okay, thanks, Michael. Fergus Harrison's appreciating the answers you've given to his questions. He's wondering if they'll be summarized later. Well, the whole thing has been recorded, so that can be played back, Fergus. And then I'm sure Michael wouldn't mind answering questions via email afterwards, of course.
And an email, the email is shown on on the presentation. I think you've got my information, but anyone who wants to send an email directly or contact me by phone is welcome.
Very good. Okay, Nicholas Yafroti has asked a question. Are you able to quantify the influence of the casing material thermal properties on the temperatures measured with the distributed temperature sensing? So I guess he's getting at what's the impact on the measurements and the calibration of the casing material. I presume he's talking about the fiber, but
I didn't understand this question very well.
So, well, assuming I'm understanding it correctly, I think he might be asking if the casing material of either the fiber itself or possibly the vessel you're measuring in? Do you quantify the influence of that? Can you work out the impact of that on what you're measuring?
Yes.
So is it altering the response rate or the actual temperatures you're measuring, and does it need to be taken into account, that kind of thing?
Depends on the application. Depends on the applications. I mean, if we're talking about in a borehole, or we're talking, you know, other industrial type applications, the fiber, especially the cable construction, is quite small to the infrastructure you're trying to measure. So
okay.
this is what we do.
Actually, Michael, he's just clarified. He's specifically after the vertical boreholes with steel or other material casing. So you're talking about the construction of the well, I suppose. Oh. And does that impact things?
Okay, I've just seen this. Look, I need to have a little bit more information to be able to answer this. I don't see the optical fiber cable will affect the temperature of the casing.
But I guess the design of, assuming I'm understanding this correctly, the design of the well,
yes,
how you're attached to whatever it is, there may be impacts of materials in between whatever you're ultimately wanting to measure and your actual fiber, I suppose.
Yeah.
Okay, so maybe that's a follow-up one.
Yes.
Then Mads Jorgensen has asked, for acoustic sensing, has Silixa experience for detecting in a subsea environment, such as by fibers in power cables? So I guess that's subsea power cables. And if you have been doing that subsea, what kind of things have you been detecting?
We have not done. We've not installed a system in subsea environments, as far as I know. The reason is I don't know about this is because a number of times we provide the DTS units, and other people provide the monitoring, the application software. Now, in projects where we supply both the application software and the DTS units, they were not in a subsea environment. Some experience we have in a subsea environment is where we have installed the units in flexible risers.
That's interesting. Okay. How deep were they?
They were not very deep, but I can't give more information about the locations, but we're talking about, I would say, 100 to 150 meters deep. But these optical fiber cables are installed. Cables can be, I mean, they can be either as a part of the bundle of the whole flexible riser, or let's say from the wells where we install a large number of cables, we can go down to 7-8 kilometers. So you can do the estimate the hydrostatic pressure the cable can sustain.
Okay. So still able to accept more questions. While we're waiting for that, I've just got a few to ask. So Michael, when these things are being installed, are they usually installed from the design of whatever it is you're measuring day one, or have people been retrofitting it? So for example, on a pipeline, do people normally buy this for the original installation of the pipeline, or have people been retrofitting it?
No, that's a very interesting topic. Now, in the installations we've got up to now, we install the cable together with the installation of the pipeline, because as you've seen from a couple of the images, the cable was dropped in the same trench. Now, we had inquiries. We haven't done any installations yet, but we had inquiries where people asked if they can retrofit the cable, and of course, for intrusion-based applications, this is quite it's a lot easier to be done, because the cable doesn't need to be in close proximity to the pipe. The cable can be installed several meters away from the pipe, because it's intrusion event. It just has to be within the proximity of the pipeline. For leak detection application, in the acoustic leak, this will work. If we want to use thermal leak, this is going to be difficult because the optical fiber cable has to be in proximity to the pipe. It has to be close.
Okay, so it's not that easy to install it then. Okay. Retrospectively.
Yes, if we use acoustic leak detection and intrusion detection, this is possible. Okay, but for thermal leak detection, it's very difficult to get very close to the pipe because the fiber has to be 10, 15, 20 centimeters away from the pipe to detect the temperature event.
Okay, thanks, Michael. Scott Lutich has just asked a question. It seems related to what Nicholas Euphrates maybe was asking. I better read this out word for word. How will the thermal conductivity of the casing affect the resolution of where the various temperatures are measured, in brackets, along the cable? I.e., will higher temperatures be conveyed along the casing due to the thermal conductivity of the caser?
No, okay, these are very, I mean, these inquiries need to be thought, okay? But let me give you an example from my experience. I've installed optical fiber cables on production tubing and injection tubing in some injection wells. And when they started injecting the fluid, the water, into the tubing, I can actually identify the clamps, okay, from the optical fiber cable, so that the temperature of the tubing inside, it will affect the clamps, and then we will see the signature, the fingerprint on the actual optical fiber cable, okay, during the ejection process. Now, if this, assuming the optical fiber cable sits between the ejection of production tubing and the casing, okay, so assuming the materials, the fluids we have in the annulus, depending on the ejection temperature, but so there wasn't enough conductivity within the process and the operation that would affect the measurements. Now, we need to see this we need to think a little bit more about this question. I'm quite happy to respond to this question later, okay, and actually get involved my colleague Craig Milne, who's looking at most of the oil and gas operations. So we can identify features that do not indicate the cable coupling temperature or heat by conduction very quickly. I mean, over long term, of course, this is going to happen.
Okay, very good. Thank you, Michael. Right, well, we're already out of time, so really appreciate your presentation, Michael, and thank you everyone for all of the interesting questions. I'll just remind everyone that a short survey will pop up at the end of the webinar. It would be great if you can all give feedback. And Michael, just to say thank you once again.
Thank you. Thanks for attending the webinar. Thanks for organizing the webinar.
Okay, we will sign off here. Okay, so goodbye, everybody.